Hello everyone. Today my topic is automatic card fraud detection based on decision tree algorithm. This paper addresses the critical issue of credit card fraud detection, which has become a significant risk for banks, financial institutions, and customers due to the rise of online transactions and card-based payment. The primary focus is how machine learning, specifically the decision tree algorithm, can be used to identify fraud in transactions with a higher level of accuracy compared to traditional manual or rule-based methods. It is important because the global impact of credit card fraud is substantial, with recent data of 2018 showing losses exceeding 27.85 billion annually. Traditional fraud detection methods are insufficient and often delayed, leading to larger losses. Detecting fraud in real time is essential for preventing financial damage, protecting customer trust, and avoiding reputational harm to financial institutions. The paper proposes an automated approach to fraud detection using decision trees, which aims to reduce the number of false positives and improve the real-time detection of fraudulent transactions. This method is intended to provide a scalable and efficient solution that can be applied across millions of transactions, adapting to different types of fraud scenarios. The main goal is to achieve high accuracy in distinguishing between fraudulent and non-fraudulent transactions using digital data and decision trees as core model. This not only helps financial institutions safeguard their operations but ensures a smooth and secure experience for the customers as well. Moving ahead, if we see the methodology, data sets are being used to real-world data sets from Kaggle. The paper utilizes two substantial data sets sourced from Kaggle, offering a large amount of data for training and evaluating the fraud detection model. Dataset 1 contains 1.3 million transactions involving both fraudulent and legitimate transactions. It spans a period from 2019 to 2020, covering transactions from 1,000 customers to 800 merchants. This data provides a good balance between fraudulent and legitimate transactions and reflects modern real-world transactions. The dataset two is even larger with 24 million transactions over multiple years. The data includes 2,000 synthetic customers. Through synthetic, it covers a wide range of scenarios, providing more examples for the algorithm to learn from and identify patterns in fraud detection. Fraudulent and non-fraudulent transactions. The balance between fraudulent and non-fraudulent is crucial for training and machine learning models. Dataset 1 contains 7,506 fraudulent transactions out of 1.3 million entries, representing about 0.58% of fraudulent cases. And dataset 2 contains 30,000 fraudulent transactions among the total entries. And this large dataset provides the algorithm with more examples of fraudulent activity to learn from, making it better fit for testing the robustness and the fraud detection model. um, the data cleaning, it is the first step in pre-processing. Uh, in data pre-processing, if we see the data cleaning in this paper, the author removed the incomplete or inconsistent transaction records to ensure the quality of training data. Missing values were addressed and using techniques such as mean substitution or removal of incomplete entries. Feature section certainly is a key feature where selected for classification tasks. These includes transaction amount, merchant details, and the time of transaction, cardholder information such as age, gender, occupation, and location, and the type of transaction, whether it was online or point of sale. These features were critical to build an accurate model. data scaling to ensure consistency across different features. The author applied the standard scaler from the scikit-learn library for normalizing features like transaction amount and time. Scaling is important because it prevents large numerical values like high transaction amounts from dominating the algorithm's learning process. Then there's training test split. After pre-processing, the dataset was split into 80-20 for training and 20 for testing. This ensures the model has trained on majority of data while still having enough data to test how well it can realize or generalize to the unseen transactions. Um, Here, the author employed a decision tree classifier from the popular Python library, scikit-learn. Decision trees are particularly useful for fraud detection because they provide a clear and interpretable decision-making process, which is important when explaining why certain transactions are classified as fraudulent. Decision trees are known for their efficiency and real-time adaptability and applicability, which means they are ideal for detecting fraud while transactions are happening and allowing for an immediate action when fraud is suspected. The transaction amount, if we see the key model features, the transaction amount was identified as most significant feature for data set 1, contributing over 70% to the model's decision-making process. The highlights that unusual transaction amounts are often a red flag or a fraud. For dataset 2, the merchant name was most influential feature, contributing to 50% of decision-making process. This is suggesting that the fraud is often linked to specific merchants or industries that might be more vulnerable to fraudulent activities. Other important feature includes cardholders' demographics like age, gender, geographic location, along with the transaction type such as online purchase, point of sale transactions. And these factors also help the model to differentiate between legitimate and fraudulent transactions. If we see the training process, the decision tree was using the historical data with the algorithm learning patterns in past transactions. It split the data recursively into branches based on the most important features, creating an hierarchical structure to make classification decisions. The cross-validation was used to uh, fine-tune the model's hyperparameters, specifically the depth of the tree. This ensures that the tree doesn't overfit the training data, that is performing well on training data but poorly on the unseen data, by balancing its complexity. The performance matrix, the paper uses following matrix to evaluate the model, that is accuracy, which is the overall percentage of transactions that were classified correctly, both fraudulent and non-fraudulent. They use precision to measure how many of the transactions flagged as fraudulent were actually fraudulent. This is crucial to reduce the false positives. Then they use recall, which measures how many of the actual fraudulent transactions were correctly identified by the model. Then they use F1 score, which is a balance between precision and recall, which gives a single score reflecting the model's performance in identifying fraud while minimizing the false positives. Then there is evaluation, which is the model demonstrated high accuracy and high F1 score on both data sets. This means the decision tree was not only effective at correctly identifying fraudulent transactions, but also managed to reduce the false positives, making it a strong solution for real-time fraudulent detection in financial institutions. Now we'll move ahead to the algorithm overview. The decision tree algorithm for fraud detection was chosen because it offers a high degree of interpretability. This means that the logic behind the decision made by the model can be easily traced, making it ideal for applications like fraud detection. where transparency is crucial. Decision trees allow us to clearly see how and why each transaction is classified as fraudulent or not. Another strength of decision tree is adaptability to handle both categorical and continuous features. So features like transaction type or the merchant name are categorical, while transaction amount is continuous feature. So the decision tree efficiently processes both types of data. In dataset 1, transaction amount emerged as most important factor, contributing approximately 71% to the decision-making process. And this makes sense intuitively as usually high or low amounts can often be red flag for fraud. For instance, a sudden large purchase on a card might indicate a fraudulent transaction, especially if it's outside the typical spending pattern of the cardholder. On the other hand, dataset to the merchant name was most critical features, contributing 50% to the decision. This suggests that fraudulent activity might be linked to certain merchants or industries, while fraud is more likely to occur. For example, online merchants or new unfamiliar stores might be associated with a higher risk of fraud. The decision tree algorithm works by splitting the data at each node based on the most important features. If the transaction amount is above certain threshold, the algorithm will branch in one direction, and if it is both that threshold, it will uh, branch into another direction if it's below. This hierarchical structure helps the algorithm classify each transaction as fraud and non-fraud based on the chosen features. The table which I have shown here features the importance of dataset 1. It shows the importance of different attributes in making the decision. So if we see the attributes, by far the most important feature contributing over 71% to classification process is followed by age uh, and location with lower weights. This means that for dataset 1, the model relied heavily on how much money was spent in each and every transaction. Moving ahead to the performance matrix, the performance of decision tree model was evaluated using several key machine learning metrics, which was commonly used to assess the effectiveness of classification models like this one. The accuracy refers to the overall percentage of transactions that were correctly classified, whether they were fraudulent or not. The decision tree achieved 96% accuracy in dataset 1 and 99% accuracy in dataset 2. This means the model made the right prediction for most transactions, but there is still room for improvement in edge cases where transactions were misclassified. So the precision is critical matrix in fraud detection because it ensures when the model flagged as transaction was fraudulent, it is correct most of the time. In other words, high precision helps reduce false positives, which occurs when legitimate transactions are mistakenly flagged as fraudulent. A high precision score is particularly important for maintaining the customer's trust, as frequent false positives can frustrate the customers when their legitimate transactions are declined. Recall, which is also known as sensitivity, is equally important in this context. It measures how well the model captures actual fraudulent transactions. A model with high recall is good at ensuring that most fraudulent transactions are detected. However, if a model focuses too much on recall without balancing it with precision, it may overflag transactions, leading to more false positives. The FN score is the harmonic mean of precision and recall, and it provides a balanced view of model performance. It particularly uses or is useful in fraud detection, where both metrics need to be high for effective detection. In this case, the model achieved F1 score between 97% and 99%, which indicates that it balances catching fraud with minimizing false alarms. The high F1 score shows that the decision tree was effective across both the datasets. If we see the figure which I have shown over here, evaluation matrix for both the datasets, you can see the model consistently performs well across accuracy, precision, recall, and F1 score, with dataset 1 yielding slightly better results due to its large data size and more varied transaction data. This suggests that the decision tree model is highly reliable for fraud detection across different types of transaction data. Moving ahead, the explanatory analysis of datasets revealed interesting patterns for fraudulent behavior. Fraudulent transactions were found to peak in specific months, particularly in March and May, followed by January and February. This shows that fraud isn't randomly distributed throughout the year but clustered in certain time periods. The POS systems and online purchases are most common avenues for fraud, indicating that these transaction types may require more scrutiny in real-time fraud detection systems. The fraud trends to improve smaller amounts, typically under 1,500 units, which fraudsters might hope will go unnoticed. In contrast, legitimate transaction can go up to 20,000 units. Age, occupation also plays a role, with those aged 45 to 50 being the most frequently involved in fraud transactions, and professions like material engineering and naval architects experiencing higher fraud rates. Interestingly, the number of fraudulent actions in here is roughly equal between male and female card holders, challenging any gender bias in fraud detection strategies. Here we can see two graphs. First one is the category-based number of fraud transactions from the first data set, which is having different modes from where they made the transaction, which is grocery POS, shopping net, net, there's entertainment, kids, pets, and health and fitness, and several others. Uh, the second chart represents the age of the victims and the number of fraud victims by the age of first data set, so which is highly between 45 to 50, and also it is moving quite a bit until the 55 kind of an age bracket, starting from 25 and until 65. It is the highest. Answering some questions here. I did find this paper interesting and well structured, particularly because it addresses an important and relevant issue, which is fraud detection in the financial industry, which is a growing concern with the increasing volume of online and card-based transactions. Actually, this paper effectively demonstrates the potential of machine learning algorithms, specifically decision trees, to improve the accuracy and efficiency of fraud detection. The strengths of this paper is clear methodology. The paper provides step-by-step explanation of decision tree algorithm along with detailed pre-processing and training processes, which makes it more research replicable. It uses large data sets with a substantial amount of transactions, which helps in training a robust model. There is a decision tree inherently easy to interpret. So interpretability of the model is very important, which I saw here is something which would make it more stronger for research. Then there is strong performance matrix. It reports high accuracy, precision, recall, F1 scores, showing that the decision tree model performs very well, especially for identifying the fraudulent transactions. The main weakness in the paper, which I have seen, is synthetic data limitation. While the data sets are large, they are synthetic. They don't capture all the intricacies and variations of real world financial data. So the real world data is often messier and a little more complex. Um, I would say that the paper does not elaborate much on the feature engineering, how the feature was selected, or if additional features could have been generated for better fraud detection. So, limited discussion on feature engineering. What would I do differently is I would try to use ensemble models. Like decision trees are simple and effective, but they are prone to overfitting. So I would explore using methods like random forest or gradient boosting, which combines multiple decision trees to improve the performance and reduce a little bit of overfitting. Um, or maybe more robust data augmentation. So I would implement data augmentation techniques to make it more synthetic data, more representative to the real world financial transactions, adding noise or variability or better simulate actual fraud behaviors. Um, Also, evaluation on imbalanced data. So, fraud detection data sets are typically highly imbalanced, with far fewer fraudulent transactions compared to the legitimate ones. So, I would try a technique like SMOTE, synthetic minority oversampling technique, to ensure the model performs well on imbalanced data set and it's not biased towards majority class. Assumptions which I would disagree with is simplicity of decision tree for complex problems. Uh, the author assumes that the simple decision tree is sufficient to handle the complexity, which I would not agree with. While decision tree are useful, fraud detection is often a very complex with evolving patterns and sophisticated attacks that might require more powerful models. And there is a lack of real-time evaluation. So it assumes that the batch pre-processing approach used in training the model will work equally well for real-time fraud detection. However, the real-time system often needs to detect fraud on the fly with very low latency, which was not directly addressed in the paper. Um, the ideas for future work or improving would incorporate real-time detection, which I mentioned prior, testing real-world data, as also I mentioned earlier that real-world data instead of synthetic data sets would give more accurate representation of how well a model would perform in practical situations. Also, explanation of anomaly detection techniques, which is incorporating unsupervised learning techniques like anomaly detection. It could help fraud in situations where the patterns are new and have not been seen before. So they'll improve the model's adaptability to novel fraud attacks. Then there is multi-algorithm approach, which could also be worked on instead of relying on solely decision trees. Uh, because if we consider a hybrid model combining decision tree, anomaly detection, and deep learning techniques to detect more fraudulent, sophisticated attacks and schemes and everything. Thank you so much. This was all from me. You can email me if you have any other questions. These are the resources for my paper. Thank you.